We're going to start for the simplest element, which is the linear plane stress triangle in two-dimensional problem. And we're going to apply what we have learned the last day. First of all, we use this triangular linear triangle element because it's very simple to explain, and because we can use it for to apply in an easy way the formulation before. It's not a very popular finite element, the linear triangle, because usually for the structural problems, the results we are going to obtain with this linear triangle are not very reliable. So usually we don't use this linear triangle for structural problems. It is more used in thermal or electromagnetic or any kind of problems, but not structural ones, not stress problem, this linear triangle. But it has one advantage, which is it's very easy to get a difficult geometry mesh using this linear triangle. So for problems where you don't need a high level of accuracy, you can use an approximation using this linear triangle. Okay, but usually in very complex problems, we usually use quadrilateral or hexahedra, which are much more reliable. If you want to get a high level of accuracy using this linear triangle element, you must use a lot of linear triangle in your mesh. Okay, but for our purpose, which is explain the formulation, it's very good because it is a simple element like this one. In fact, we have more than one kind of triangle element. We can name this Turner triangle, which is defined by 3 nodes placed in the corners. These are the connection nodes. Remember, we are talking about a discretization space. So we can discretize this domain using this triangle, and the connection nodes are placed in the corners of the triangle. But we have another kind of linear triangle, which is, for example, the Bobek triangle, where the connection nodes, which is where the primary variable is placed, are located in the midpoints of the triangle. Remember that our primary variable are the displacements in our structural problem, but usually the thermal problem will be the heat or temperature or any kind of problem. This primary variable will vary, will change. But in our case, displacements are our primary variable. So our information is placed in these connection nodes, and this Turner triangle has this primary variable placed in the corners of the triangle. Okay. So the geometry is defined by these coordinates. The primary variable has got 2 degrees of freedom for any node, so we have 6 degrees of freedom placed in these 3 nodes. And in this triangle, we must talk about the geometry and the primary variable. So we must finally interpolate these 2 functions, displacement function and geometry function, using these coordinates. This Bobek triangle has the geometry defined by the coordinates of the nodes in the corners, but the primary variable is placed, the information, the nodal values are placed in these midpoints values here, named 4, 5, or 6. So 99% of the problems with linear triangle use this Turner triangle because its properties, taking into account the convergence requirements, are better than this Bobek triangle. So let's talk about this linear triangle called the Turner triangle, where besides the geometry and the displacement, we're going to use the geometric feature, which is the area, and this area is calculated using these geometric coordinates in the nodes, and this area has got a sign, it's a signed magnitude, and that's why we use a convention, which is the coordinates and of the nodes, and the numeration of the nodes is placed in a counterclockwise sense, which is the one you see here. So this 1, 2, 3 numeration of the nodes must be in this counterclockwise sense, so that the area is calculated with a positive number. So geometry, area, and displacement function are calculated into this triangular domain, and for that we are going to use we're going to talk about these triangular coordinates. For now, they are only triangular coordinates. They are only a geometric parameter in our linear triangle. These triangular coordinates, T1, T2, and T3, are the geometric feature of this triangle defined in this way. For every node, 1, 2, and 3, we have a triangular coordinate calculated as a coordinate for every point in the triangle. Every point in the triangle has one T1, T2, and T3 coordinate, taking into account that this triangular coordinate has got value 1 in the node, in the corresponding node, T1 to node 1, and 0 in the opposite side, that's side 2, 3. And this triangular coordinate varies linearly, considering this parallel straight line here, using this notation, considering this 1/2 for the distance between this parallel side to this node 1. So consider this, imagine this median line from this node 1 to this midpoint, and this distance, 1/4, 1/2, and 3/4, defines this triangular coordinate for this node. So every point in the triangle has got one T1 triangular coordinate, which defines his distance toward this node 1. Remember that here in this node 1, this triangular coordinate is 1 always in the node, in the corresponding node. The T2 triangular coordinate, same thing, is 1 here in this node 2 and this 0 in the opposite side, and it varies linearly from node 2 and this opposite side where T2 is 0, and same with node 3 where this triangular coordinate is 1 and 0 in the opposite side. So imagine that for every point in the middle of the domain, we have 3 triangular coordinates, which, for example, in the nodes is 1 and 0 in the opposite side. Imagine, for example, this midpoint in any of these 3 straight sides has got 0 triangular coordinate for T1, 0 triangular coordinate for T2, and 1/2 for T3. Okay, so every midpoint of these 3 sides has got the same combination of triangular coordinates, 0, 0, and 1/2. And for example, the centroid, the center of gravity, let's see, the center of gravity, which is the intersection of the 3 medians of the triangle, has got 3 triangular coordinates, 3 equal triangular coordinates, which are 1/3, 1/3, and 1/3. Okay, so these sort of natural coordinates, independent of the geometry, taking into account that these triangular coordinates are independent of the coordinates of the 3 nodes, define the position of any point in this linear triangle. And these triangular coordinates must accomplish this consistency condition. They accomplish this consistency condition, which is for every point of the triangle, the addition of these 3 coordinates must be 1 at any point. So we are able to characterize, to locate any point at the triangle element using these triangular coordinates. But the point is that usually we work with Cartesian coordinates. Most of the magnitudes we're going to work with, they are expressed in Cartesian coordinates like strains or stresses or whatever. So we must use an expression, a relation between these triangular coordinates and these Cartesian coordinates. And these are the relation between these Cartesian coordinates, these triangular coordinates. So we are going to interpolate these Cartesian coordinates using these triangular coordinates between 0 and 1 using this expression. This first row is the consistency condition, okay? And this second and third row are the interpolation to calculate these 2 Cartesian coordinates using these 3 coordinates of the 3 nodes and these 3 triangular coordinates we have presented before. these expressions can be inversed, and the inverse relation between these three triangular coordinates and the Cartesian ones are this expression here. We're going to use this expression here in a moment, and to define this matrix here, look, we have this kind of terms and this kind of terms in a simplified way, in a simplified notation. We express this triangular coordinates relation using this subindex, where this y23 and x23 represents this this rest between y2 less y3. This is y23, and the same with the x. And here, this product here is called this area defined by these two nodes, these four coordinates, and we call it in this way. A23 represents this double product between x and y, changing the subindex of the two variables. So now these triangular coordinates are expressed in a simplified notation using this matrix here. Okay. So this dependence between these two coordinates are expressed in this way in the two sense, depending on the coordinates of the nodes. And now we can calculate these partial derivatives for the coordinate transformations. We need these partial derivatives because sooner or later we want to calculate this strain displacement matrix, these partial derivatives, and we are going to see what happens, which problems we are going to find when we try to calculate these partial derivatives in Cartesian coordinates. Remember that most of the things are expressed in Cartesian coordinates, but our functions usually are expressed in these triangular coordinates. So if we remember the expression before, these derivatives, these partial derivatives from the Cartesian to these triangular coordinates here are these ones. So remember, partial derivative of x with respect to the t 1, 2, or 3, we use this first matrix equation here. Let's see. Here. So these are the independent variable, these are the coefficients. So if we calculate this derivative of x with respect to any of these three triangular coordinates, we find these three coefficients, or these three coefficients, if the partial derivative is a partial derivative of y variable. So we find just a coordinate with these partial derivatives. And if we want to calculate the opposite, the inverse partial derivatives from triangular coordinates to Cartesian coordinates, so we can see this matrix, and we want to calculate this partial derivative. What we obtain, remember this triangular coordinate is this line product from this first row and this vector. When we calculate this partial derivative with respect to x, we find this coefficient, and the partial derivative with respect to e, we find this coefficient. We have notated these coefficients in this way. So these partial derivatives of the triangular coordinates are expressed with the same notation as we have seen in the matrix before. Remember that this subindex e varies from 1 to 3, and this j and k subindex are the cyclic permutation of this index. So for example, for e equal to 1, j is equal to 2 and k is equal to 3, or the direct permutation when e equal to 2, j equal to 3 and k equal to 1. So we have three cycle permutations for these three partial derivatives, respect to x and respect to e. Same thing. If we look at the third row here in this matrix expression, relating the triangular coordinates and the Cartesian coordinates. So now we are able to calculate these partial derivatives, and all of them are expressed in terms of the nodal coordinates x, y, and this xj less xk, and same thing with the x. So that's partial derivative depends only on the nodal coordinates of the three nodes of the triangle. So imagine that we have any function f, let's say f, depending on these triangular coordinates, any of them. In general, we're going to call it f. We can calculate this derivative, this partial derivative, with respect to Cartesian coordinates, which is something we are interested in. And these derivatives, using the chain rule, taking into account that this x is expressed in terms of triangular coordinates, this partial derivative is expressed like that. Here we have the derivation of the function with respect to the triangular coordinates, and here we have this partial derivative from the of the triangular coordinates with respect to the Cartesian coordinates. So again, this partial derivative with respect to the Cartesian coordinates is expressed using these nodal coordinates, and this partial derivative of the function with respect to the triangular coordinates, because we are going to find this expression here sooner or later. We're going to see in a matrix form these two derivatives, these two partial derivatives here is expressed like that. So for any kind of function expressed in triangular coordinates, this multiplication between these nodal coordinates and these three partial derivatives with respect to the triangular coordinates, and this is a factor, this is the area of the triangle, they are expressed in this way. Okay? So let's see what are we going to to calculate using these partial derivatives. For example, we are going to consider a displacement function interpolation. So imagine we have a displacement function defined in this domain, this triangular domain, for any point, and for any point we have 2 degrees of freedom, characteristic of the plane stress problem, and these 2 degrees of freedom, ux and ue, is interpolated for every point using these triangular coordinates here. So in the way that finally we can express this primary variable, we are not talking about geometry now, but the primary variable using this interpolation expression here. These are 3 nodal values for the horizontal displacement. These are 3 nodal values for the vertical displacement in the 3 nodes, and we calculate any displacement, horizontal or vertical displacement, for any point using this interpolation here. Okay, so we use these triangular coordinates to interpolate the primary value in this way. If we want to express this in matrix form, let's consider that these T1, T2, T3 triangular coordinates for the 2 degrees of freedom placed in this way. We have this N matrix, and we have these 6 nodal values, 6 degrees of freedom in our triangular plane element. So in fact we are using these triangular coordinates as a sort of shape functions. From the beginning of the class and up to now, I said nothing about the shape functions. I was talking only about triangular coordinates. So our triangular coordinates, which are geometric parameter of the element of any triangle, even if we are not talking about finite element method, we use these triangular coordinates as an interpolation function. That's the shape function, which leads us to an expression for the displacement at any point of the domain. So here you have one representation of a shape function, for example, n1. n1 is a function which has 1 value in this node 1, 0 value in the opposite corner, and it varies linearly along the domain. And this is valid for all the 3 triangular coordinates. N2 and N3 are the triangular coordinates. This is something that characteristic from the shape functions. It is 1 value in the corresponding node and 0 in the not only the opposite side, but in the other nodes, which is not node 1. And this is something triangular coordinates accomplish perfectly. So that's why we use these triangular coordinates as a shape functions in our interpolation procedure. So now we came to a definition of the stiffness matrix and the magnitudes we're working with. That's strains, stresses, or displacements. We said last day that kinematic equations related the displacements and the strains using partial derivatives. So imagine that we go to the last day and remember this expression here, this strain vector. Remember that strain vector has 3 components for the plane stress problem, or for a plane problem, even for plane strain problem, related with the displacement using this D and this N matrix. This N matrix is this D matrix is the partial derivative matrix. This is the shape function matrix, and this is the nodal displacement vector. We have 6 degrees of freedom, so this nodal displacement vector has 6 components. So now we come back to this nodal, to this N shape function matrix, and we want to calculate the derivatives. Remember here, these derivatives here are derivatives with respect to the Cartesian coordinates. So we want to get the partial derivatives of this N matrix with respect to the Cartesian coordinates, and we use, in fact, we use this expression here. Okay. Remember that this derivation, these partial derivatives here, are constant values because we have linear expressions for this triangular coordinates interpolation. So this derivation of these shape functions are these constant values depending only on the coordinates of the 3 nodes of the triangular element. So the strain expression is this strain displacement matrix. We know about this matrix, and these nodal values, 6 nodal values that characterize the strain for any point of the triangle. Remember that these are constant values. This is a very important point. These are constant values, which means they are not depending on the point. They are not depending on the triangular coordinates. They are partial derivatives, constant values, and depends only on the coordinates of the nodes. Remember, we have a constitutive equations. For the plane stress, this is the constitutive equation, which relates these 3 components of the stress and 3 components of a strain. And these are the stress and strains characteristic of a plane stress problem. Remember that we have the tensorial component is the distortion divided by 2. So here we have this double, which is the distortion, the total distortion, which is related to the tangential stress using this. Using this coefficient here. So finally we get the relation between distortion and this tangential stress. This is the elastic matrix for plane stress. Remember that for plane strain we have a different elastic matrix, even if the problem is the same. Just changing this elastic matrix, you change the problem from plane stress to plane strain. Even you can change not only the matrix, or not the matrix, just the values of this Young modulus and this Poisson coefficient. Just changing these expressions here, you can use the same expression for the elastic matrix, for the plane stress and for the plane stress problem. But anyway, we have a relation between stress and strain, which is expressed in this way: elastic matrix times this elastic strain vector. And finally, we come to this stiffness matrix. This is the stiffness matrix we have obtained in the last class. It was expressed in terms of this B strain displacement matrix and this elastic matrix and this thickness. This is the thickness of the plate for a plane stress problem. And now, if we place the results we have obtained in the last slide in this integral, we're going to obtain this sort of result. Let's see. Here we have, okay. I told you that this B strain displacement matrix is calculated using, departing from the partial derivatives, and these partial derivatives are constant values. They are not depending on the point on the triangular element. They are not depending on triangular coordinates or Cartesian coordinates, or they are constant. They go out of the integral. So we can't take out this B strain displacement matrix and the elastic matrix. So in a linear triangular element, the result for the stiffness matrix is the one we have in this slide. So this is the thickness. We can consider a variable thickness, but usually this thickness is constant. But the point is that we are able to obtain this stiffness matrix in a closed form. Closed form means that this is the expression for a stiffness matrix. You don't have to make any integral as long as the stiffness must be integrated, but not due to the B strain displacement matrix of the elastic matrix. This is the area of the triangle. Usually, and even for the plane stress in plates, we consider this thickness as constant. So we can take it out from the integral, and we can simplify this expression for the stiffness matrix. So here we have a stiffness matrix expression in a closed form. This is not depending on the coordinates for a linear triangle element, which makes it quite easy. It's easy to implement. Just it's a question to implement these values, these elastic values, and these nodal coordinates, and you will have easily a stiffness expression for your linear triangular element. I underline that this is a particular case where when the dH is constant. Okay, this is a very particular result because this is not the common result. It's not very common that you get a so easy and so close form stiffness matrix when you make an integral. Second hour of the class, we're going to see what happens when calculations gets much more difficult than for a linear triangle element, and what happens with these integrals. Okay, so but now, for now, take this into account. This is the result of applying what we have learned about the total potential energy minimization to get the stiffness matrix of a problem applied of a particular linear triangle element. And for a consistent nodal force vector, we can find similar conclusions where this this shape function matrix are expressed in terms of the triangular coordinates. So this consistent nodal force vector is calculated in this way. This is the integral. We assume B is the body force, per unit of volume. If we assume these body forces are constant, we can take it out of the integral, and this is the nodal force vector. Nodal force vector here when body forces are constant, taking into account that if we calculate the integral of these triangular coordinates, this integral over all the domain is known, is the 1/3 of the area. 1/3 of the area of the triangular element. We can see this result if we look at this shape function. Imagine that you must make this integral of the volume under the shape function. So this is one value, okay? This is 0 and 0, and this volume is 1/3 of the volume that you could build if you place this one value and one value in these nodes. So imagine we have a parallelepipedic figure with one value in the height. So this volume you are looking at this slide is 1/3 of the area times 1, okay, which is the value in this shape function. So that's why all these three integrals are 1/3 of the area. So for a constant value of the body forces here, these body forces come out of the integral. Same thing with the thickness, and this is the result for a nodal for a consistent nodal force vector of the external forces, okay? Which is the same result as we could have